All right, to start out here, I want you to look at this pattern and see if you can answer the question. So it says, how many triangles will be on stage 9? Explain your reasoning. So if you look at it, right, stage 1 has 1 triangle. And if you're counting, stage 2 has 1, 2, 3, 4. Stage 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9. And so on. So we want to figure out stage 9. Pause the video for just a second, try it, see if you can figure it out, and then come back and we'll try to look at some of the patterns. The answer is 81. So some of you may have figured out, if you did another one, that on stage 4, if you add another row of triangles, it ends up being 16. Stage 5 ends up being 25. But if you look at the pattern, this goes up by 3. The number of triangles goes up by 3 between stage 1 and stage 2. Then it goes up by 5. And then it goes up by 7. And then it goes up by 9. And now we can start to see a pattern where each of those are in the differences, or the amount of increase is going up by 2. The other thing you may have noticed is that if I take a stage number, right, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. This actually is what we call a quadratic pattern. You guys last year spent a long time looking at linear and exponential patterns. You may or may not remember, linear we called arithmetic, and exponential we called geometric, but you looked at a lot of those patterns. What we're going to do today is take those patterns that you already know, the linear and exponentials, and compare them to quadratics patterns. So in your notes, you can pause this video and copy this down really quick, but these are the 3 different types of functions we're going to look at. So when you look at a linear function, so make sure you have all this in your notes. If you look at a linear function, it looks like that is going to be, the graph's going to be a line. And the equation we use, if you want to find the equation of the line, is this y equals mx plus b. Just a quick reminder that m is the slope, and b is the y-intercept. Exponential functions, they look like the graph below. So they come in along the x-axis and then they curve up, and they start increasing more and more quickly. A is the y-intercept. And then b, right there, is what we call a common ratio. And just to remind you really quick, when you look at a quadratic, to get from one term to the next, here's an example of a quadratic. Like I could go 1, 2, 4, 8, 16. So what you're doing each time, right, is we're timesing by 2 to get the next one. Well, that number you're timesing by is what's called the common ratio. And then quadratic functions, right, this is what we've been talking about for the last while. The highest power is a 2 if this forms a parabola right there. So again, what we're focused on is just taking these different, giving information about the function, deciding if they're linear, quadratic, and exponential. And then we're also going to actually find the equation of the functions also. Here's some examples. So let's do this example A. So the directions say, plot the points, tell whether the points appear to represent a linear, an exponential, or a quadratic function. So A, the point is at 4, 4. We got 2, 0, 0, 0, 1 and a negative half, that'd be somewhere in there, and negative 2, 4. And hopefully, when we see this, most of us are recognize this is just a parabola. So if we're asking what kind of function is it, we're going to say that it is a quadratic function. And it did not ask us to, but we're going to find the equation too. So the equation, if you can tell where the vertex is, which in this one we can, right? That's my vertex. Then we can just use the vertex form. Y equals a times x minus 1 squared minus a half. Now all I have to figure out is what a is equal to. We could plug in another point to do that, but one thing we know is if I go from the vertex, if I go over 1, normally it goes up 1. I'm only going up a half. So right there it tells me that a is going to be a half. So there's our equation. Y equals a half times x minus 1 squared minus a half. Okay, let's try B. So B we're going to plot those points. We got a point at 0, 1, 2, 4, 4, 7, negative 2, negative 2, and negative 4, negative 5. Okay, hopefully that makes it pretty clear what the pattern is. This one is linear. We could find the equation of this one too, right? We do the y equals mx plus b. So m is the slope. So if I count the slope, it's going up 1, 2, 3, and over 2. So the slope is 3 over 2. The y-intercept is right there, right? It crosses at 1. So that would be the equation that fit those data points up there. Let's do this last one. So it's asking again if it's quadratic, linear, or exponential. So let's plot the points. So we've got 0, 2, 2, 8 would be somewhere just right up there. 1, 4, negative 1, 1, and negative 2, a half. Okay, so you look at that shape. Sometimes it's hard to tell the difference between exponentials or quadratics by looking at the graphs. But we're going to assume if it doesn't curve up, that it's going to keep coming, it's going to have that horizontal asymptote. So we're going to say this one is exponential. Now let's see if we can come up with the equation for this one too. So we use that y equals a times b to the x. A is the y-intercept. That's just 2. So y equals 2 times. And then b is what you're multiplying by to get to the next number. So if you look at your y values, it goes, we're at 1 here, then it goes to 2, and then to 4, and then to 8. So we're multiplying by 2 each time. That means my common ratio is 2. If you wanted to, you're fine leaving it like that. If you wanted to, we can use our exponent rules to combine those. That'd be y equals, and if you times things at the same base, you add their exponents. So it'd be y equals 2 to the x plus 1. Those two problems are, those two are the same thing. So you could write it either way. All right, so we can look at, we can plot the points and we can tell if it's linear, quadratic, or exponential. We can also come up with the functions. Sorry. It turns out there's another way to also check. So I'm gonna skip past well, actually, let's do one of these. So I'm gonna look at this one right here, and it says the same thing, to plot the points and tell what they are. I'm not gonna plot the points. What I'm gonna do instead is just put them in a table. And when I put them in the table, I'm going to write the x's in sequential order. So what I mean by that is I got the negative 1, 5. Then I'm going to go to 0, 0, negative 1. Then I go to 1, negative 3, 2, negative 1, and 3, 5. So if you look at these x's, they're in sequential order, negative 1, 0, 1, 2, 3. So if you can put those points in it, if they are in sequential order, you're not skipping any x's, we can come over here and we can look at the y coordinates and you can figure out what pattern it is. So what I'm going to do is I'm going to look for what's called the first difference. And all I'm doing is looking at the y's and checking to see how much they're going up or down by. So if I'm going from 5 to negative 1, it's going down by negative 6. Then it goes from negative 1 to negative 3, it's going down by 2. And then from negative 3 to negative 1, it's going up by 2. And then from negative 1 to 5, it's going up by 6. Well, you may or may not remember this, but if it increases or decreases by the same amount, so that first difference is the same, then it's a linear pattern. These don't. This is not linear. What I can do then is I can check what's called the second difference. And what I do is I take the difference of the differences. What I mean is I look at these right here. I look at that first difference, and I want to find the difference of those. So I'm going to go negative 6 to negative 2 is increasing by 4. Negative 2 to 2 is increasing by 4. And from 2 to 6, it's increasing by 4. Hey, what that means is this is quadratic. So whenever that happens, we say it has a quadratic pattern. That's when the second difference is the same. If I ask you to find the equation, I'd have to know where the vertex is. If you look at the y values, it goes 5, negative 1, negative 3, negative 1, 5. That point Now that -3 is in the middle of the y values. You can see the symmetry there. So my vertex is going to be y equals a times x minus 1 squared minus 3. Now we can figure out what a was by plugging another point in. But here's another really cool trick, is if I come over to that second difference, a will always be equal to half of whatever that is. So it's half of your second difference. So if my second difference was 4, half of that is 2, I automatically know what 2 is equal to. That's not the only way to get it, but that's just a little trick here where you can come up with it pretty quickly. All right, let's try this next one. Let's do the same thing. So we're going to make our table. I'm going to write them in sequential order. So I think -3 is the first number. It's 32. -2 is 8. -1 is 2. 0 is a half. And 1 is 1/8. All right, if I check the first difference, now that's going down by, what is that, 24? That's going down by 6. This is definitely not linear. That's going down by 1.5 or 3 halves. Oh, anyway, that's going down by, what is that? 4/8 minus 1/8. It's going down by 3/8. So this is not linear. We could try the second difference. That's going up by 18. That is not going up by 18. That's not going to be the same. That's like what? 4.5, 4.5. So this is not linear or quadratic, which leads us to believe it might be exponential. Here's how you check to see if it's exponential. You got to look for that common ratio. So you're going to take this and always take, you're going to take 8 and divide it by 32. So 8 divided by 32 comes out to be 1/4. So you're timesing by to get from 32 to 8, you're timesing by 1/4. And then take 2 and divide it by 8. 2 divided by 8 is also 1/4. So you're timesing by to get from 8 to 2, you're timesing by 1/4. Then you could go a half divided by 2. That's a little tricky, but the way you divide by a fraction by 2 is you times by its reciprocal, so that you get 1/4. And each of those has a 4, so 1/4 is your common ratio. That means that this is exponential. So let's write our equation. It's going to be y equals my y-intercept, which is right here. It's at a half. So y equals a half times by my common ratio, which is 1/4 to the, I'll put that in parentheses, because we're going to raise that to the x power. So I have my equation. I'm going to skip past that next one, but let's add this to your notes. Go back up to where we wrote linear, quadratic, exponential, and we showed the graphs. Write this down. So under linear, next to linear, we know it's linear if the first differences are constant. We know it's exponential if they have that common ratio. You're timesing by the same number each time to get from one y value to the next one. And we know it's quadratic if the second differences are constant. Now, this is really important. For this to work, the x value, it has to be consecutive x values. What I mean by that, if you go back up here, right, when I lined it up, it went -1, 0, 1, 2, 3. I didn't skip any numbers. They were consecutive x values. This one went -3, -2, -1, 0, 1. They were consecutive x values. So if you're checking for the first or second difference or the common ratios, you have to make sure that the x values are consecutive right there. So consecutive x values. All right, so if you need to pause it, write down those. Those will be important things to know for linear, exponential, or quadratic. It's the part that I have highlighted there. All right, so let's just try maybe one more of these. So I'm going to go down to some of these. We have some tables here. I'm going to say are they linear, exponential, or quadratic. We'll do an example of each.